So it turns out the reagent lot change is not the only thing that can cause the QC values to change when the patient values are not affected. Things like maintenance, component replacement, or deterioration of an analyte in the QC material can all have a similar phenomenon, and all of us have probably observed that. So when these occurrences happen, and you see a QC shift that you can't figure out what caused it, make sure to use patient samples to determine whether or not it was real or not. If it was determined to be not real, then make the adjustment. And this is a diagram. I'm not sure the final version that's going to be in the C24 document, but this is close to it. So this is a two-step process. So when you change reagent lots or you see another change that doesn't make any sense, base your decision on whether or not it's real on patient sample comparisons. Look at the average bias between the conditions. If that average bias is less than a critical difference that is going to affect patient care decisions, then you have to stop and fix it and don't report patient results. Step 2 is if the answer to the bias being greater than that critical limit, then you look at the QC values. Is it different from the current value? If it's not different, you continue. If it is different, you make that target value adjustment, and now your QC rules will be effective, just as effective as they were before, at identifying the stability of that measurement procedure. So a corollary to this is obviously QC materials are not used to verify the agreement of patient results between different reagent lots, except when the QC materials are provided by the manufacturer of the measurement procedure for that stated purpose. And there are instruments on the market that come with something that is used to confirm the performance. And the manufacturer in that case has taken into account these types of adjustments that may occur. So this is, I was told I'm the only guy with an equation on here, and I usually hate equations, but the equation is not the important thing. The equation is in the document, and it's in textbooks. The important thing is when you're determining a cumulative standard deviation, you need to take data from within a reagent lot. If you cross reagent lots, you're very likely to have this artifactual change give you too large of an SD, which means you're fooling yourself with respect to your QC rules performance. So there's a formula for pooling across different reagent lots or different conditions. You can see the formula here. Not going to spend any time on it. So the next step in the process is to set goals for QC performance. So now we understand our measurement procedure. We have very good SDs and target values to use. So the goals for performance, as Kurt has already said, are based on the total allowable error for medical decisions made using that test result, and based on performance capability of a measurement procedure. And we always have to consider the risk of harm to a patient from an erroneous decision being made using a laboratory test result. So it's really important to remember that quality control cannot improve the performance characteristics of a measurement procedure. It is what it is. The important thing is to know what it is. An inadequate measurement procedure, however, can only be improved by implementing a new measurement procedure. If we don't have a better one available, the measurement procedure performance is going to influence the QC strategy. And we'll get to that momentarily. So, establishing a QC strategy based on performance goals. The QC strategy is these 5 main components. What concentrations are we going to use? How many different concentrations? So we're going to run 2, 3, or more concentrations. How many measurements on each concentration? We ordinarily make 1, but there are situations where we might consider making 2 or more. There are QC rules that have to be determined, and there's a QC schedule that has to be established. So the strategy considerations is we want to detect an out-of-control condition that's large enough to cause a hazardous condition with possible patient risk. We want to minimize the frequency of false QC alerts, because that wastes everybody's time. And we clearly want to minimize the number of potentially erroneous patient results before the next QC event. So let's talk just a minute about performance goals. What I've shown here is a diagram that shows the distribution of the variability of a particular measurement procedure, the typical Gaussian distribution with a target value in the middle, compared to the total error limits for that A measurement procedure. In this case, we have what can be referred to as a 6 sigma method. And what that means is the variability of the measurement procedure is much, much less than the total allowable error needed to make solid medical decisions. In that situation, if we have a small change in performance characteristics, it's very unlikely to actually affect results that are reported out of the laboratory. So we can use less stringent quality control. Less frequent rules like a 1.3s or a 1.4s may be quite satisfactory. On the other hand, if the performance characteristics of the method are barely adequate within the total error allowed, sort of a 3 sigma method as this particular diagram demonstrates, that same change is going to have a very large number of results exceeding that upper total error limit in this example, and that's not good. So we need more stringent QC to make sure we can identify much smaller changes before they become medically important. So the QC rules themselves are based on the SDI or the Z-score, as I mentioned in the beginning. There are counting rules that everyone's familiar with. For example, the 1 result exceeding 3 standard deviation intervals, 2 exceeding 2 standard deviation intervals, 2 out of 3 exceeding 2 standard deviation intervals. These are examples of commonly used counting rules. There are combination rules. The most well-known is probably the range 4S rule. But others that are becoming more and more useful as computers become more and more powerful in our laboratories is the mean of the standard deviation intervals, the moving mean of those intervals, exponentially weighted moving average of the QC values, or the cumulative sum of the SDI values. These lend themselves very well to trend detection, much better than anything else that we've had available to us in the past. So just to illustrate one of these, I'm going to show you how the QSUM rule operates. So what I've shown here on the bottom here is a half of a Levy-Jennings chart with the SDI values associated with each point. And you can see about halfway through a trend of increasing values begins to be noticeable, but it never exceeds even 2 SDIs. At the top are the parameters for the QSUM. So we're going to do the QSUM calculation if we exceed a 0.5 standard deviation interval. And if we accumulate enough to fail 3, we will fail. So let me show how it works. So there's the first time we have a 0.5, and the calculation is you subtract the trigger value, so it's 0. Next time you take the value of the SDI, subtract the trigger value, add it on, it's 0.1, 0.2, etc. But now we no longer trigger, so we're starting to go back to 0. And at this point, we're starting to see our trend, and you can see how the values just accumulate. You add them onto each other until eventually you exceed whatever threshold you've established. That's a QC alert. Now, establishing the threshold can be done to give you a heads up for trend detection early, where you may not even need to stop, but you can take corrective action, or when something more severe, which means stop what you're doing and fix it. So it's very powerful, and the exponentially weighted moving average and the other moving mean approaches all accomplish the same thing. It largely depends on what software you have available to you, what you can do. All right, rules performance. So historically, the power function graph had been used as the basis for determining how well a given QC rule works. And there are computer simulation software packages now available from several different vendors that can do a very good job of saying if my performance characteristics are this, what's the performance of different rules combinations, and you can select good rules combinations based on that. You can also do an empirical assessment. And since this is probably a newer idea, I'm going to talk a little bit about it. So this is relatively straightforward. You take a large series of QC results from a period of stable performance and you put them into a spreadsheet. You can say, I want to evaluate the performance of a particular rule, let's say a 1.3s rule. Well, you can just run that rule against all that QC and see how frequently it gives you a false alert. Then you can introduce a change of a stated magnitude, say a change that you want to definitely be able to pick up because it's going to be medically meaningful, and then determine how frequently that rule identifies a change. And you can go through this process relatively easily on a spreadsheet and figure out your rules combinations without computer simulation. Well, however you choose to figure out what rules to use more than one. Multiple rules have been a mainstay of laboratory medicine forever. And I should say since Jim Westgard published the first paper on the subject. Here's a typical example of a combination that's not infrequently encountered. A 1,3s followed by a 2,2s, a range 4s, and maybe a cum sum or moving average of some type. Now, to talk about the QC schedule, there are different kinds of measurement strategies in our laboratories. The first is a batch. A batch is defined as it has a defined starting and stopping time. So we're going to load, let's say, something onto an HPLC measurement. We start it in the morning, we put our samples, we put it on at the end of the day, or later that day, we get the results off. The recommendation here is simply run QC at the beginning and the end of the run, and you can determine if every value during that run is likely to be correct. If it's a really long run, you might want to run some in the middle, or if the measurement procedure is a little bit unstable, you might want to run some in the middle. Continuous measurements. These has become common in our laboratories, particularly in the high volume chemistry, hematology environment. A series of measurements continue indefinitely until some event occurs, such as reagent replenishment, maintenance, or calibration. This situation, we need to figure out the frequency to run QC consistent with the risk of a hazardous condition from potentially erroneous results actually causing harm to a patient. So this is what we talk about. So the minimum regulatory requirement in the United States is once a day. We have to give some serious consideration to whether or not that's actually adequate. So we can use less frequent QC measurements when we have good analytical performance relative to the medical needs, or high sigma methods, if you use that terminology. Or we want to use more frequent measurements when the measurement procedures have marginal performance relative to the medical requirements. We have to talk about critical control points. These are scheduled events, things like maintenance and recalibration. The event may alter the performance condition of the measurement procedure. In fact, we do maintenance to alter the performance characteristics, to put them back to as new condition. In this situation, we should run QC before the event to confirm there have been no changes since the last acceptable QC value, and after the event to confirm the event itself didn't cause a problem. Because just because you recalibrate doesn't mean it recalibrated correctly. So to summarize this chapter, we need to define the quality requirements based on medical decisions and measurement procedure performance. Select QC materials, determine SDs and target values that adequately and correctly represent measurement procedure performance, set our goals for QC performance that consider the risk of harm to a patient, and then establish a QC strategy based on those performance requirements. So, thank you for your attention. And there's a bibliography for your information, several book chapters that reflect some of these same concepts.